Hi everyone, welcome to today's webinar. Today we have Dr. Long Yi to share with us about her research on smart materials and smart devices. First, let me briefly introduce Prof. Long Yi. Prof. Long Yi graduated from University of Cambridge. Her research focuses on smart materials and devices, thin film technology, energy-saving materials, and functional nanomaterials. Her early career started with successful lab-to-fab technology transfer to industries including Seagate technology. She published widely as last corresponding author in Science, Chemical Society Review, Materials Horizons, and ACS Nano. She is also the chief editor of the book, The Monochromic Smart Windows. Her work was highlighted in Nature and was reported widely by Reuters, Agence France-Presse, Channel News Asia, and many others. So now I'm going to leave the stage to Prof. Long Yi. Prof, you might start.
Hi, hello everyone. Yeah, very nice to meet you online. So it's 4 o'clock already. You must be very tired. So I just explained to the panelists, I'm trying to make this talk more or less like a storytelling instead of talking too much technical details, because I think many of you may not doing the same research as mine, because my research is one of the less popular one in material science. Okay, so anyway, so thank you very much for Institute of Advanced Studies to invite me to give this talk. So my topic is responsive materials, so from energy saving window to smart devices. So this will be my content. So you can see a large proportion of my talk is about the energy saving smart windows. Okay, so you can see this will be the part 1. Then I will move to this stretchable, the electronic and artificial muscles. This will be the smaller ones. Okay, so for the first one, for the energy saving smart window, so why I spent my last 10 years. Okay, so here I'm sharing with you my research stories of this studying with one student and minimum like resources just for 10 years ago. So how can I accumulate all this knowledge to become one of the leading scientists in this field? Okay, so first let me introduce where is the big picture. Okay, so this is the background. So can you see here? So you can see the building. So when I first saw this one, I was also felt quite surprised, even shocked, you know. So among all these energy consumptions, right, 40%. So this is a very alarming figures, right? The 40% is coming from the building energy consumptions. Okay, among this 40%, 50 is coming from this air conditioning, ventilation, and the heating. So you can see this figure is really huge. And also in buildings and window, we always say window is the least energy efficient part of buildings. So that's why people do a lot of work on this smart window. So like Prof. Lee from my colleague, she spent a lot of time working on this electrochromic, and Prof. Inje from US, he spent some of his efforts doing this microchromic, smart window. And there's another one which is photochromic. Photochromic is less used in this what we call is energy saving smart window, because the working mechanism is not that rational. So I am the one working fully focused on this thermochromic, which means it will change automatically with the thermal input or stimulus. So, and also there's another thing here. So you can see I can read through. This is from DOE, Department of Energy in United States. And what they said is what the estimated is. In fact, in the United States, the nation's total primary energy consumption was about 97 quads. So this is total, including everything like industry, everything. Okay. But can you imagine that while the window associated energy consumption in buildings was estimated at about 3.95. So when I saw this one, I thought, wow, my research is really, really meaningful. So, right, which means the window associated energy consumption is about 4% of the total primary energy consumptions. This is really a very alarming figures. So that's why I said, hey, I'm just very lucky because I could spend my last 10 years to work on this field. Okay, so this is the big picture. So that's what I always start with. So as I just mentioned, so there are 4 types of a smart window: electrochromic, thermochromic, mechachomic, and photochromic. So of course, I'm dealing with the thermochromic. I have to say it is the best, right? So first of all, is because actuation is passive, which means it will respond to temperature automatically. Passive means automatic. That's very nice. Right? So automatically, which means we'll save a lot of cost. And the stimulus, which is thermal, not like others, you need a very complicated structures. And also the device complexity is very low, and it's very simply just use some coating, and encapsulation is good enough already. Like electrochromic, I know like Prof. Lee is doing, Prissy is doing like electrochromic, they need many different layers and make the structure very complicated. And it's very good for this energy-saving windows. And the speed is acceptable because it's not like an optical device, right? You need like less like second. For this one, it doesn't matter, even 10 seconds, 1 minute, it doesn't matter because it's for window for this energy saving. Okay, so some of comic enjoy this passive thermal stimulus, which we call it's a rational stimulus, and very simple structures and very suitable for the energy-saving windows, and the optical speed is good enough. Okay, so this make this thermochromic is one of the very good choice for smart windows. And for the thermochromic smart window, there are also different types such as hydrogel, ionic liquid, metal materials, perovskite, liquid crystal, and vanadium dioxide. So vanadium dioxide is one of the more conventional ones. So later I'm going to spend some time there. So you can see we compare a little bit of these 5 here. So you can see, so these are the thermal or responsive materials like hydrogel, as I mentioned, ionic, metal, perovskite, liquid crystal, and VO2. So if you're interested in this area, so you can read through my paper on this one. So we have compared the good and bad thing of different materials. Okay, so you can read through. Myself very much focus on the vanadium dioxide and also the hydrogel. Okay, so that is where I'm from. So smart window is that we have electrochromic, thermochromic, photochromic, mechachomic, right? So I focus on the thermochromic. So even thermochromic, I only focus on the VO2 and hydrogel instead of like perovskite, liquid crystal, and ionic liquid. Okay, so these are the two the big pictures. Okay, so I only talk about these two materials. Okay, VO2 and hydrogel. Okay, so why we talk about VO2 and hydrogel? Okay, so first of all, start with VO2. So VO2, like it's a thermochromic oxide. So because we undergo the semiconductor to metal transition at a certain temperature, so there's quite a few ceramics, like these few all can have this semiconductor to metal transition. But why VO2 is so popular? So if you read a science paper for the last 20 years, you will see a lot of VO2 have been published in science. Okay, simply because VO2 can change its phase from semiconductor to metal at only 68 degrees. 68 degrees, which means it is very close to room temperature already, right? So saying if it's very close to room temperature, which means will be very readily used for many applications because it's about change. Device is about change, right? You give them an input, the output have to be different, right? So if something is close to room temperature, that make this VO2 a very much wanted and loved materials in research community, not only in thermochromic oxide. Okay, but anyway, so just let you know, VO2 is because of this requires a near room temperature phase transition from semiconductor to metal, and they change from rutile phase to monoclinic phase. And rutile, it is more or less like high temperature, so it's a metallic phase, and monoclinic is a room temperature phase, so it's a semiconductor. Okay, so simply by changing the temperature, and remember, it is only 68 degrees. It's wonderful, wonderful materials. Okay, and the other one is hydrogel. So you can see the hydrogel, right? So hydrogel, why people use hydrogel? You know, nowadays a lot of research groups have used hydrogel for all sorts of different things. So we use hydrogel because of this requires a phase separation. So which means if you heat up, right, some of these polymeric chains is going to collapse out of the water. So in my research field, I want to use this what we call a collapse of this polymer. So because then this one is going to serve as a scattering center to scatter the light. Okay, so this we use a phase separation. So you can say these two working with different mechanisms. So VO2 is phase transition, and hydrogel is working with phase separation. So again, give you this is a very typical vanadium dioxide optical response. You can see this is when the temperature is lower than this transition temperature. So you can imagine this is more or less like winter time, right? The winter because the temperature is low. So winter time. So this is the curve. So you can see all the light below here can get transmitted. Okay, and the summertime will be something like this. So this is a very typical vanadium dioxide optical responses. Okay, so when the temperature is higher than tau C, because it change of phase, right? So you can see the transmission is below the area below this curve. Okay, so the transmission below the curve, it is much reduced. So this is very good, right? Because the good thing, number one, is because so both winter and summer, so you can imagine the blue one is below the transition temperature, so winter and summer. So both of them can keep certain luminance transmission, which means because no matter what, you're doing glass, you're doing window. So window, why you use window, right? Because people can still see, right? Can see through, you need transparent, and also it can give you the luminous transmission, which means you don't need to turn on the light all day, right? Like daytime, you can use a daylight, okay? So this is what we call luminous transmission. So a good smart window, you need pretty high luminous transmission. And at the same time, so obviously, if we talk about the energy saving, right? So you want as much transmission as possible for winter. Am I correct? Right, to warm up the house, right? And in summer, you want as little transmission as possible. So which means the difference of the transmission between the low temperature and the high temperature, we call it a delta T so, which is the transmission difference, solar transmission difference. It need to be as high as possible. So that is why we put these three things here. Number one is tau C, because remember, right, VO2, although it's good, it's 68, it's good enough. But for window, it's better to be at least keep to room temperature. Actually, very recently, I reviewed the paper for Drewer, the claim that the best temperature is about 20 something, 28. So I'm not sure at this moment because I just reviewed. But anyway, trying to reduce this tau C is one of the big things in vanadium dioxide. And also that's trying to make the TU as high as possible and delta T so as high as possible. So as any other research, you always have some, we call it a performance index. The performance index. Okay, so these are the three performance index we are very much wanted in the thermocomic smart window. So I know many of you are not doing this research. Maybe you can just write somewhere, okay, because you have to get familiar with these terms, otherwise it will be difficult for you to follow later. Okay, tau C, luminous transmission, and the delta T so, okay, which means the transmission difference. Okay, so remember this one, reduce tau C, increase luminous transmission, increase the transmission difference, the modulation, we call it a solar modulation capability. So obviously more in winter and less in summer. So which means the difference between summer and winter, the higher, the better. Okay, so all these are the big pictures. So let me move on. Okay, so as I said, I started in 2011, so about 10 years ago. So we at that time read this paper from the NanoNH. So they said, okay, remember this is delta T so, right? Delta T so and the TU. These two things need to be as high as possible. Okay, so obviously the best one is at this corner, right? This corner. Okay, so the solar modulation, which is delta T so, and this is visible transmittance. So if you don't do any modulations of your manipulation of your structures, you will be here. So for example, I just coat a single layer of VO2 on top of glass. So this is the maximum data I can get. So it's pretty low. You see, the delta TSO is less than 10%, and the visible transmittance is less than 20%. That's horrible. Okay. So scientists spend enough time to solve this issue. They propose like porous structures. They propose like a multilayer structures, porous structures, make it porous, right? And the multilayer structures, and also the composite structures, which means the VO2 is not a continuous field anymore. So VO2 is introduced as a nanocomposite, like nanoparticles inside it. So all this is continue to make improve the performance. As I said, the best one is here, right? The higher, the better. So at that time, roughly the best reported TLU is about 40, delta TSO is about 22. Okay, so we start from here. So this is as I said, when I start my research in this field, so this is what has already been done in the research community. So then, of course, as a researcher, right, you always want to do new things. Okay, so as I just mentioned, so people use multilayer, people use porous structures, people also use these nanocomposite structures. Okay, so to enhance properties, because TLU and delta TSO, it's very difficult to enhance it at the same time. So we spend a lot of time. So for example, like make it biomimetic structures, like gray structures and photonic crystal structures, like all these structures, we're trying to enhance its properties. Okay, so this is what we have done with VO2. Okay, then, okay, we realize no matter how hardworking we are, it is very difficult to continue to improve this TLU and delta TSO. So we are the first in the research community trying to use this hydrogel. So hydrogel. So you know VO2 is inorganic, hydrogel is organic, right? So we are the first one to use some because everyone is doing inorganic. So why not we try some organic things? So we're the first one trying to use this hydrogel in the smart window. Okay, as a material scientist, the next step is trying to hybrid that. So then we have this VO2 and the hydrogel, we hybrid them together. So we also have one of the films produced from these two. And then because as I said, so VO2 and hydrogel are both passive, but in many applications, people want it to be active, which means I want to control. I want to make it this way and that way. I want to take the control. Okay, so that's why we also have another way we call it active control. Active control, because VO2 and hydrogel is passive, but I want control it by myself. Okay, so that's why we propose this electro-thermochromic, which means we combine with electrochromic, and together we come up with electro-thermochromic concept. And also further on, we also combine with Nikkei thermochromic. So these two concepts. Okay, so you can see this one will become active control. Okay, so and further on. Last year, we say, hey, hydrogel is quite difficult to make it uniform. There's a lot of issue there. So how can we further to improve? So we come out the first smart liquid windows, so which is hydro liquid. Okay, so hydro liquid windows. Okay, so these are the ideas we have contributed to the research community. So as I said, we come also from very humble beginning. So at the very beginning, we don't know much, like only one PhD student. So we work very hard trying to, at the very beginning, follow what other people have done, and one step by one step, come out our own ideas. Okay, so we also start with very humble beginning, but the thing is, our group works so hard, and we generate many new ideas in this field. Okay. So first of all, let me just focus on the VO2 quickly. Very quickly, as I said, just a storytelling. Okay, so the phase change we have let me talk about VO2 first, then hydrogel. Okay, so VO2, right? VO2. So we trained a lot of these biomimetic structures, for example, like MOSI structures, because MOSI have this anti-reflective functionalities if you give them certain structures, and also these photonic crystal structures, make it more like a butterfly, have different colors. And also very recently we published one, we mimic this green brittle auto is by anti-reflective structures. So this one, you can see this is a very transparent butterfly. Okay, so the butterfly is transparent because of, again, some unique structures. Okay, I very quickly go through what we have done. So this one, we work with Jilin University in China. They gave us some like tapered structures. So we study the periodicities with optic response. We realize if the periodicity of such structures is less than 200 nanometer, it's around 200 nanometer. So we can get both enhanced TLU and delta-T at the same time. So this is the very first biomimetic thermocomic smart windows. Okay, so it's the first one. Of course, at that time, it's a very, as I said, it's a humble beginning. Okay. So then Yujie worked with BGU, our collaborator from Israel. So we said, because some customers said they don't like vanadium dioxide, the color, because the color is more or less like brownish. So I personally think the brownish is quite nice, but they think a brownish is not nice. So they want to change the color. So we use this, as I said, the butterfly, right? The photonic crystal structures. So we use these silica spheres assembled on top, then just coat VO2. So then you can see we can change the color. So so if you don't do anything, it's brownish color, but we can change like more reddish, greenish, or whatever. Okay. So these are the method. Okay. And you can see, right? So this is also the simulation suggesting this color change is coming from the reflection. So 400, something like reddish, 600 bluish, and 700 like greenish. Okay, so we use a very complicated way trying to understand how we can change the color of this VO2 by using this butterfly, the photonic crystal structures. Then we continue. Okay, so the IBS, my PhD student, and he read something about this transparent. You can see this butterfly is very transparent. So why the butterfly is transparent is because the butterfly also have these taper structures, but different from here, right? Different from this ideal, you can see all these taper structure, they're very ordered. So for example, 200 is 200, 300 is 300, 1 micron is 1 micron. So all these are fixed. But for this, what we call is a ghetto, this butterfly, why they're transparent, and also the anti-reflection is the same from all different angles, is because they also have these taper structures, but the periodicity and the height are very random. So we're trying to mimic these structures. We're trying to find a very unique way to do it. So we just simply like a 9 silver nanowires on top, use this as what we call is a template rows, then guided by template goals, then you grow whatever things on top. So they will borrow this template, grow these tapered structures. We have tried our VO2, we also tried silica. So we try to different two materials trying to test these ideas, because we want proof this is a very universal way. So you can use it for these anti-reflective structures. So we have done a lot of characterization saying this anti-reflection is useful, and this is very simple because this is a bottom-up way, and also is angular independent. Okay, and also the good thing, it can both enhance TLU and delta T at the same time. So if talking about the smart windows, okay, so this is one of the latest paper. And then we also come out these graded structures. We start with simulation, work with a physicist from BGU. So we say if we make them these graded structures, we can get much enhanced TLU and delta T at the same time. Okay, so this is just a theoretical paper. And then this my student, she went to the BGU, so Huji in Israel, working with a Professor Mandela, using this electrochemistry way, and they're trying to deposit this whatever like VO2, even the deposit, they try to make it a little bit more universal, such as a CNT, 1D, graphene like 2D, gold nanoparticles 0D, and two different things on top of these graded structures, make it graded and prove that it works for this concept. So which means once you get graded structures, you can also enhance TLU and delta T at the same time. And also this, I always boast these papers because it's done by my undergraduate student, just a final year project. And he just spent, he's a same young scholar, he spent about 3 months and come out a very simple way. You know, undergraduate, right? They do simple things. Okay, they just use more or less like a mesh printing. Then this mesh printing, they have used different kind of mesh and just a drip drip printing, whatever, with VO2 inside, and then we'll follow this, we call it a self-assembly. So you can get all sorts of structures and periodicities, and they also prove that compared with other ways, so you can also both enhance TILU and DLTs at the same time. And this is highlighted as a back cover for an undergraduate student. So this is his first authored paper. And then Vijay also continue to work on, because we realized that VO2, right, a lot of people doing this, we call it a plasmonic resonance, LSPR. But LSPR, everyone know that it works only with metallic states, right? Metallic state, okay. So, but the good thing, if you still remember, VO2 is going to transit from the semiconductor to metal phase. So which means if we also make this VO2 more or less like nanoparticles or like a nanoparticle arrays, we will also find this LSPR, but it is tunable, because it only when happens at metallic phase we have this LSPR. Okay, so why we need to do so is because we need shift to the dense solar energy area. So we ignore the details. There's a lot of work here that you just spend a lot of time like trying to fine tune the different process, because we're material scientists. Okay, so a lot of experimental and lab work, trying to control the viscosity, the plasma etching time, and also the different precursors, so that he can get all sorts of structures like nanoparticle arrays, like nanodome and nanonet. And he focused very much on this nanoparticle arrays, like nanoparticle arrays. So he reported this LSPR switch on and off, because as I said, if it's a metallic phase, only this LSPR only happens at the metallic phase. So switch on and switch off. So this is definitely one of the very first. Okay, because all the other people talk about gold, silver, but we talk about the tunable LSPR. And continue, then we also think we still very much have to focus on smart windows. So we said once we use this way, we can both enhance TILU and delta T cell at the same time. Okay, so and also Vijay continue work a little bit more theoretical, in-depth theoretical calculation with Prof. Sun Zhimei from Beihang. And he trying to understand the substitutional dopants, oxygen vacancy, and surface oxidation effects on these plasmonic effects. And there's a lot of theoretic work here, so I'm not going to talk about in details. So you can, if you're interested, so you can read through these papers. So it's a collaboration with Prof. Sun, and she's a theoretical calculator, calculation. She's from the calculation side. Okay. So, and also Vijay has demonstrated there's record high tunabilities for localize the LSPR, the NH from 0.66 to 1.16, right? Because we keep saying we can tune this LSPR, right? So this is one of the highest record high tunability, and also the transition temperature is, the interval is 60 degrees. So all these other record high results. Okay, and we demonstrate the usage in smart window, variable camouflage, and this SIRS, and in krypton inks, all sorts of things. Okay, so it's, as I said, VO2, later we'll share with you, VO2 is so versatile. It's one of the very most versatile materials in the whole world. Okay, so then we write this review paper together with Prof. Gao Yanfeng, because in 2012, I start from his review paper from Nano Energy. So finally, after about 10 years, we rewrite this review paper together with him, and we're trying to review it from this electronic state to atomic state to this nano scale, then micro scale, then real building scales. So the scale, different scales, we see how VO2 can really be used in this real buildings. Okay, so we stay in such a scale way, and we also summarize the properties. Okay, because as I said, so we need enhanced TILU, enhanced delta T cell, and reduced tau C. Okay, so these are our, so obviously the better here, right? Okay, so what we have done, so before we join this field, so people have done single layer, people have done composite, have done these multi-layers, okay, but we introduced the gridded biomimetic structures, and you can see all this tipped one, all these are the record high samples, and this tipped one is from my group, okay? Okay, so now I move to the hydrogel. So since, as I said, after like 3 or 4 years, we realized, hey, it's really difficult to continue to improve this TILU and TISO. So what can we do? So yeah, obviously, as a material scientist, everyone do the organic or inorganic. Maybe we can try organic. So we start from this. The first, it's a very simple paper. So we simply just drip hydrogel liquid and then laminate between the glass. And by simply control its thickness, we can get all sorts of different optical response. So this is the very first hydrogel smart window in research community. So this is the first paper. And as I said before, so it's worked with this phase separation concept. So you can say the concept is very simple, right? So you can imagine this is winter time and the summertime, if you control the different thickness, so you can control either from very opaque or very translucent. Okay. The good thing is because now you can tune this visible range. This is a visible range. VU2 only tune in the IR range. Okay, but the hydrogel more tune in the visible range. So you can see compare with VU2, right? So the average TILU is about 60 and the delta TISO is about 12. But if I use hydrogel, I can get this one nearly double, delta TISO from 12 to 20, and the TILU is from 60 to 70. So get both much enhanced. Okay, and also we work together with Prof. Shlomo in Fuji University, Israel. We're also trying to print this hydrogel on top of some of these transparent electrode. Okay, so this is one of the printable. We call it the hydrogel is fully printed, and we're trying to hybrid with silicon luminant gel and print it on whatever substrate to make all sorts of shapes. Okay, and the second one is we said before, so that you can see the red color one is typical VU2, and the black color one is typical hydrogel. So if you hybrid them, so you can see this is a blue one. So the blue one, so you can see both of them, the visible range and IR range can open up. So this gives us a record high delta TISO. Now you can see the delta TISO, if you still remember, in 2014, this record is about 22. So now we can move to 34. Okay, so we break the record, as all of you do with your own little research area. Okay, and then a lot of people start to do the hydrogel, but hydrogel have problem, because it's very difficult to make it uniform, because as I said before, I have experience with industry lab transfer. I have transferred the technology to Seagate before, so I know how important the upscaling, how important make it large scale still very uniform. So I think, hey, since everyone is doing gel, because gel is very difficult to make it uniform, so why not we make it as a liquid? So liquid can flow everywhere, right? So which means it doesn't matter how big your window is, you can make it very uniform everywhere. And no matter how big the size is, right? Okay, and also, we also find out that water, because hydrogel, large amount of the hydrogel is about water, the component is water. And water have this, what we call is intrinsically very high specific heat capacity and very high thermal energy storage capabilities. So why this one's important, later I'm going to explain. So for the first time, we combine another functionality is what we call the thermal storage. The thermal storage, these functionalities with thermocomic smart windows. Okay, so you can see, right? So as I said, very simple ideas, right? So we just make a liquid. It's not a gel anymore. So we just pour between the glass panels. So you can see I'm standing behind, I'm 1.6 meter. So this one, the glass is 1 by 1 meter. So it's very simple, very uniform, right? So when the temperature is low, so it is transparent. Okay, so if temperature is getting higher, like more than 30 degrees, so it's getting either translucent or opaque, right? So we solve this simple because the journals, they love the idea, whatever things, if you make it big, they will be very happy, because which means you don't have problem to face the industry scale up. Okay, So this is a very important thing if you're doing research, you know. So your lab is very easy, right? You make 1 centimeter by 1 centimeter sample, looks nice, no problem. You do SEM, TM, looks perfect. But you cannot transfer such technology to industry. So the industry are very interested in this, what we call is a very large scale technology, okay? Very simple concept. We are very happy with this work, okay? So, and also we have to emphasize this a new concept here. So because of this heat storage capability, because remember, right, we said water itself is going to hold the heat. Is one of the intrinsic properties of this, store the heat inside the water. So you can see we can generate what we call a peak shifting. So why peak shifting is important? For example, I'm just giving you give you some like a quick explanation. For example, if I simply just use this about normal glass, right? So for example, in Singapore, so it's about 12 o'clock. So everywhere is going to get a peak, am I correct? So which means all the windows is going to get the highest temperature at 12 o'clock. So which means this 12 o'clock is the usage, the peak usage of any electricity. So obviously the electricity, the bill will be the highest one, which means the charging will be the highest one. But if we find some way to shift this peak to some like other time, like 2 o'clock or 3 o'clock or 4 o'clock, whatever. So we can just make this peak using time to a cheaper period. For example, like now people encourage you wash your clothes during nighttime, right? Because nighttime, the electricity actually is cheaper. Okay, don't use it like in daytime at daytime because you're fighting the electricity with industry, with the office. But if you wash your clothes in the nighttime, actually the electricity bill is supposed to be cheaper. Okay, so that's the good thing about this peak shifting. Okay, so and also we done a lot of calculation with civil engineering person. We say, hey, compare with pure liquid, pure water, and no-e glass, we can save a lot of energy, up to 30%. Okay, and also the other thing is we have also demonstrated that compared with the double glazed glass, we also enjoy a lot of this, what we call is a soundproof. The soundproof effect. You can see this one is a soundproof. Normal glass is here, and the noise reduction window is this, we call it a double glazed glass, and our window can even enjoy higher 50% more of the noise reductions. Okay, so you can say it's a very simple ideas, and they can be published in Jewel, a top journal, and also it's interesting and useful. So many people, so many industry partners look for me. They want to commercialize this into the market. Okay, so this is a very first smart windows. Okay, I have to move fast because I think I'm okay, only 20 more minutes left. Okay, now I move to the active control. So this is again very first one. So we work with a Prof. Shunomo from Huji University. So he gave me this a transparent electrode. This is copper. So called copper. Okay, so actually it's transparent. Okay, it looks if you see such it is transparent, and also it is conducting. So we simply just use Joule heating. So if we don't give them any current, so it is still very transparent. But if we give them a little current, so you can see it becomes translucent because the current gives the Joule heating. Okay, it's a simple concept. So then we continue. And then we said, okay, compare with other things, we have very much enhanced this, what we call is a transmission contrast, and also the response time with all these reported other references. Okay, and then we continue to work on, because we want to make it more or less like printable, because we're not only satisfied with this hydrogel printed on this transparent electrode, we hybrid them, because hydrogel is organic gel, right? It's water-based organic gel. Then we hybrid them with silica aluminum gel. So this is more or less like a silica gel. Okay, we hybrid them. We borrow the strings of this silicon aluminum gel. So then this hydrogel can solve the problem of this what we call a fragile characteristic of hydrogel, make it printable. Okay, and also at the same time maintain its smart functionalities. You can see if we change temperature, you can also change these optical responses. Okay, it does not influence the optical responses. Okay, so you can see we printed such a silicon aluminum and also hydrogel, this the hybrid gel. So on top of this one is copper on top of copper. So you can see there's no short circuit, right? Very interesting, right? Make it very bendable and flexible. And also we even can twist it, make it more or less like a light guide. This one we call it a light guide. Okay, and also we compare, if we compare with other electrochromic, because electrochromic is more popular now, it's more mature technology in market. So we say compare with other like electrochromic materials, we enjoy the fast response time and lower applied voltage. Okay. And then Dr. Ije, and he come up with a new idea of active control of this mechanical and thermal stimulus responses. Again, this is just ideals, because we say, hey, it's so difficult to continue to improve this Tiru and delta T so why not we trying to use some mechanical ways? So for example, in this case, right, you can imagine winter more or less like this, summer more or less like this, okay? So we use this, we call it a kirigami structures, okay? So you cut in different ways, you can get different patterns. So by using this, combine this mechanical way, so we can further enhance this Tiru and delta T so at the same time. Okay, so you can see we demonstrated, you can see, for example, right, without this kirigami, so your summer is here, winter is here. Okay, but with kirigami, your summer is still here, but your winter with much more enhanced transmission, right? So for this state, so this is state 3 is what we wanted for winter, and compare with, you can see we compare with panophones with only LSPR, with only kirigami. So this LSPR plus this kirigami is going to get both enhanced delta T so and Tiru at the same time. Okay, so you can see these are some summaries compared with the other work. So this is Tiru and delta T so. So this is experimental results, and these are the simulation results. So we are far better than even the simulation results. We also have done a bit of energy simulation. So we set in Hong Kong and Houston and Madrid. So both can enhance this Tiru, and the energy saving is better. Okay, and also there's another concept, because we're trying to mimic this what we call squid. Why squid can change color, right? Because when it's under attack, so the skin is going to shrink, right? Because very nervous, so the skin is get shrinked. So on this the skin of this squid, right? They have this what we call this grating structures. This grating structure, once get a squeeze, so you can see the periodicity gets reduced, right? So by doing so, automatically the squid can change its color. So this one is another, we can also categorize as biomimetic structures, but I put it together as an active control here, okay? So the thing is, we use this concept and we add one more functionalities for this smart window. So we have a privacy window and also the energy saving windows. So for example, so you can see, so maybe it's easy I show you this window, this video, so it will be easy for you. So you can see this is stretch state, right? Stretch state. Okay, so it's transparent, right? But if I put it back, privacy. Right, this is privacy, and the other mode is transparent, right? So you can see the thing is, it doesn't matter it is privacy mode or it is non-privacy mode, the energy saving is still the same. So we use a concept. So what is this concept? Because what your eye can see, right? What your eye can see is actually a pointed. It is a pointed light, which means when the light is straight, your eyes can see. Your eyes cannot see this as scattered light, but actually your body can feel is this scattered light. So we simply use the difference here. So what your eyes can see is either privacy or it is non-privacy, but this privacy mode does not influence your energy saving mode, simply because even the light gets scattered, okay, it still can go into the room, warm up the room. Okay, so that's why we said we separate into this mechanical chromic and thermal chromic, okay, by giving them different stretching. But this mechanical and thermal actually they work independently, okay, which means your mechanical only change the privacy mode, but it does not influence the energy saving mode. Okay, so this is very much wanted in the real applications. Okay, so this is another biomimetic and also active control. Okay. Okay, so now I move to what's the next. Okay, so since all this so far, 1, 2, 3, based on what people have already done, based on we said the big three things: to reduce Tausi, to improve Tiru, and also at the same time to improve the delta T cell. Okay, so that's the very fixed performance index for this field. Okay, so what's the next? Okay, so the advanced energy materials invited me to give them a review. So we said, so in the perspective, we said, okay, so number one, trying to break the boundary between different categories. For example, we have already combined with electrochromic, right? We also combined with this Mikai comic. So we have already combined with these two, as I reported, okay, active control, right? So this, we have already done some of this work, break the boundary between different categories, and the customer design, and also scalability and durability. So no matter what, we are doing window research. The window, once installed, cannot take it out, right? So it's 20 years lifetime. So scalability have to be very easy to scale up, and high durability is 20 years, okay? And some multifunctional design, and have to consider the heat transfer through the windows, okay? So let me try so to give us a cover report, and we're trying to see here we can combine everything on the window, because as I said before, window itself consumes about 4% of the total primary energy in the whole world. Always bear this figure in mind, 4%. So it's very alarming. Okay, so this one is a customer design. So basically, right, before, when people doing this thermochromic, they just every time assume this light, no matter winter and summer, it's just one angle. Okay. But because I was from China, so I know when wintertime, the light is get much more tilted. So we simply just use this way, use the 3D printing, simply just make the sunlight coming more tilted for winter, but more blocked in summer. So it's a very, very simple concept. Okay, so we're trying to use this one, which is more realistic and more customer designs, okay, for different attitude. So you can give them different tilting, maximize this energy saving. So this is the first one. The second one, so as I said, VO2. People love VO2. You will see a lot of VO2 science paper. Okay, but VO2, unfortunately, it is a thermodynamically unstable phase in the room temperature. It is unstable. So if you want to use it, trying to solve this issue, the unstability issue. Okay, so Zhou Xing is one of my collaborator and also the visiting students from Sichuan, and they come out this way, trying to work on this, use this the PVD way, and come out a very simple idea. Use this rapid thermal annealing. Trying to deposit this VO2 still embedded in V2O5 and V3O7. Why this one is good? Because V2O5 and V3O7, these two are the thermodynamic stable phase at room temperature. Room temperature. Okay, so by using a very special way, they're trying to get a very durable VO2 films, and these films have very good thermochromic property, number one. At the same time, the service life can be even more than 20 I can't remember exact value now, should be more than 20 years. Okay, but for normal VO2, if you put outside for 1 day or 2 days, it's going to fade already. Okay, just 1 day or 2 days fade already. So you can imagine how unstable this material is. But for this film, right, it is also very accidental, it's because he came to my lab, he bring the sample, and we measure for him. See here why. This sample, even after 1 year, still have very, very high thermochromic properties. So it's more or less like an accident, So you see, then we realize, we do the TEM, so we realize this VO2 is more or less like embedded inside V2O5, amorphous V2O5, because V2O5, it is very stable. So that's why it can enhance its durabilities. Okay, so this is another one, durability, trying to solve the durability issue and the scaling issue. So number 4, the multifunctional design. Okay, so we're trying to work together with solar cell people, because a lot of solar cell people work on this transparent solar cell, right? But actually you have to be very careful with solar cell, because so for example, you put solar cell on top of the Singapore's roof, right? Because most solar cells are very absorbing. So if they're very absorbing, which means they're going to incur a lot more heat on the buildings. So which means they're going to increase the heat burden, heat load on the buildings. So there could be one possibility is the power generated using solar cell may not even compensate for the extra air conditioning because of this extra heat loading. Okay, so please bear this in mind. Okay, so most of the time when we do research, right, we only talk about ohm, but actually you have to talk about more like integrations. So anyway, the other thing is because like an urban city, you have so many window area. So why not use this window? Number one, we have energy generation. Okay, and number two, we still enjoy this energy saving. Okay, so we have done a bit study and together work with a group from China. So we have come out this table saying, hey, all these actually are very large papers like Nature Nature or True or very top journals. Okay, so we reported that if it's only transparent solar cell, right, the PCE is roughly here. Okay, and AVT is average visible transmission, like some, if you PC is high, normally AVT is low. Okay, for this one, so this is a Nature NH, so you can see, so the AVT is high, but the problem is the PC is low. And also the other thing is nobody talked about energy before, because energy saving before. They only talk about it can use to generate electricity. But how about the heat incurred there? Okay, so you have to be very careful. So there's no modulation at all. So we report a new way, so which can gain, first of all, a good like PCE, not bad, right? 16.1. But I'm very sure there's some solar cell. I'm not a solar cell person, so that's why I have to work with expert. So this we can get 16.1% PCE. The AVT also 25. I think it's pretty good, right? And also it's flexible because we put on a flexible on a polymer substrate, and also durability is good. And also we gave them this durability, the modulation in NR range. So you can see the comment here is with high PCE and reasonable AVT, we have good flexibility, we have good this durability, and also what's the most important thing is we consider this energy saving. Okay, so you have to consider these two together. Okay, so this is our TOC. So basically, this concept is use the visible range. So the visible range is used for the energy generation, because solar cell is working with a visible range, right? And also use this visible range to gain the lighting. You can reduce the lighting, okay? And also at the same time, because most of this NIR range is not modulated, but as we said before, it's better winter is this and summer is this. Okay, and the last thing is this, we call is this long wavelengths, because long wavelengths we call is just like Louis glass. Okay, we need to use a Louis glass. We're trying to make this form, which is more or less like thermal insulation. Okay, so you can see we use a different wavelengths and doing different things. Okay, this one is energy generation, this is energy modulation, and this is energy insulation, heat insulation. Okay, different wavelengths for different things. Okay, and what we do is we use this, again, we use view 2 together with purpose guide, blah, blah, blah. So you can read through by yourself. And these are the characterizations of the of these solar cells. So then we said the thing is, you can see here, if we put our coating on this surface, okay, on this surface, okay, so we can, number one, so we can get much reduced, because most of the solar cell, they use ITO, right? So the ITO intrinsically have very low emissivity, which is long wavelengths from this 2.5 to 25, this microns. So it's intrinsically, it's a low E. Okay, so we can have, by doing so, we can get, if you compare with this, let's say the last one here, or this one. So if you compare with a commercial low E glass, okay, so you can see the energy efficiency with VO2 or the without VO2. So with VO2 is here, which means the one with VO2 is the lowest one, which is the most energy saving one. And also the solar generation, right? So if I put this purpose guide without VO2 or with VO2, so you can see if with VO2, so in both Singapore, Atlanta, and the Tuska, so both of them, is going to get enhanced because the PCE is higher, which means your energy generation will be higher. Okay, then we add up this energy saving and energy generation, these two together. So you can see. So compare, these are the net benefit, which is one side is you have generated extra energy, right? At the same time, you have saved extra energy. So these two add up together. So you can see with this VO2, so we can get much more the net benefit in different regions compared with the perovskite, the normal perovskite without VO2. Okay, so this is something very recently published about 1 month or 2 months ago. So let's continue. Okay, now I move to the last part already because I think I'm running out of time. So I'm trying to finish everything. Okay, so if you still remember this graph, right? We said, okay, these are the big three things for this for the research. Okay, the reduced toxicity, enhanced human density. So, but actually the problem is this is not enough. This is not enough, okay? For a very long time, for unknown reason, people never talk about this region. Never talk about this region, which means 2.5. So everyone just talked before 2.5 microns. But from 2.5 to 25 microns, nobody talked about it before, okay? The thing is, for an ideal window, you have, because this portion we call is for reduced cooling. And forgive me because I don't have time to explain details. So you just simply need to know for an ideal case, in winter, you need as much solar transmission as possible because this is for the heating, and as low as possible of this requires this emissivity to suppress the reduced cooling. Okay, but summer is the opposite. Okay, so for the first time, we add another performance index here, which is data emissivity. Okay, so how can we realize this? We use a very simple way. So we just turn the glass. Okay, so in summer we make the one with high E facing the outside. In winter we just turn over for this low E facing the outside, because this is a proof concept. So you can see this, we have realized this one, right? You can see this is a visible range and a solar modulation range. This is this long wavelength range from 2.5 to 25. So you can see, so we said once, okay, remember this is a new performance index. Once we introduce this new performance index, which is data emissivity for this long wavelength IR, so you can say even though this new work, although the TLU is lower, the delta T is even lower, right? But once we have a new performance index here, so you can see we have calculated energy saving in Singapore, Carroll, and the Shanghai. So we can, in all different places, so the energy saving compared with this field work, this work, actually all this work are from my group, okay, it's because we are the leading group in the whole world, okay. So okay, so all can enjoy more than 10%. Least is 10%, high is 21%. So which proves the importance of this new performance index, which means we tell the research community, hey, not enough, it's not enough. Don't just focus on TLU and delta T. So this is not enough to gauge whether your window is good or not. Okay, please add one more, which is this data emissivity, some emission modulations. Okay, so this one is a new performance index. So let me continue. So my other students also, they're trying to work something which simply work on Singapore. So with a very high radiant cooling, transparent, the proof that works. And then our latest one, actually this one was accepted by Science. Yeah, it has not been published. So it's the first time I talk about it to public. So again, it's the same concept, but remember this one, right? Okay, number one is you have to turn. You have to turn, right? Which means winter, you have to turn the window, because the review, actually this paper was reviewed in June. It was rejected. It's because people say it's very weird that you turn the window, right? But actually I saw it in Germany, okay, but it doesn't matter anyway. So the best thing is if you can make it passive. You can make it passive, okay? So again, and also we said window, it is you have to be visible. So this one you have to be visible, and also summer and winter, you have to switch switch. So you can see window actually is the most difficult and most complicated cases, okay? And we come up with a very simple concept here, you can see. So we simply just use solution weight, just spin coating. We come out this concept and trying to make, you can see. So this one you have to be very familiar with already, right? This is a very typical view tool, very typical view tool. So if you don't do any structure modulation, so this long wavelength, it is always very high, which means at any time you always promote this relief cooling, okay? But the thing is, as I said before, if the ideal case is summer is high, but something here, which to the ideal case. Okay, so that is our work, and this is some like image. So I just, and also we have done a lot of calculation together with Pop Town from US. We said once using our materials, we can in general, in overall the world, so we can save up to more than, I can't remember exact values, the energy saving all over the world, because this is the first switched everywhere is modulated according to the best condition. Okay. Okay, the last word, oh goodness, the view tool is really lovely. It's because of this phase change. It can be induced by heat, by temperature, by magnetic, by this force, by electricity, by everything. And that's why it change can be used. It's such a versatile material. It can be used everywhere. So very recently, we published one with one group doing this durable inverted. It's against a solar cell, but we also add them view tool. We give them a lot of good properties. So I ignore the details because I'm not the last corresponding author here. So we just, you can read through if you're interested in this paper. Okay, the last one. Okay, so we work together with Xiaodong because this one is not my main work, but we're still trying to put everything together. So it just happened because my student put his hydrogel into the salt, then realized, hey, the hydrogel become very stretchable, you know, very so then we work together with Prof. Xiaodong and trying to use this more or less like artificial muscle. So you can see this one, right? So it can conduct, it can stretch much better, and also at any time, right? When you stretch, so you can always have this ion conducting. Okay. Okay, so this one, so we use, it's a very simple way by simply soaking the hydrogel in a salt. So we can get one of the highest stretchability, one of the highest toughness, and also the highest ion conductivity, which is perfect for these artificial muscles. Okay, and also my colleague, Dr. Hu Hebing, he come out a very simple way, just stirring. So if you're interested one, you can talk to me, okay, just stirring. So because we are very poor, I'm a very poor research group, you know, so we can only use very simple ways to do research, okay? So just use a magnetic. So he trying to turn this silver nanowires, so trying to just deposit it trying to what we call it's layer by layer growth, which means now you can see the single nanowires is more or less on one direction, right? Because of the shear force, but you give them a shear force, so they think the nanowires can just align with certain directions. Okay, so this is one direction, then we do the vertically one, and then they stretch it. Okay, so this is also a very interesting one. So by doing so, we get the highest transmittance, because if you just randomly just spin coat whatever silver nanowires on top of any transparent substrate, so it will become very, very random, right? So you block a lot of sunlight, block off of visible light, and also the conductivity will be much reduced, right? Because you have many things just touch together. Okay, so you're going to reduce this conductivity. So by doing so, simply we call it a monolayer assembly of these silver nanowires. We get one of the highest conductivity, highest visible transmittance, and highest stretchability. So we compare with all the other categories such as CNT and graphene, like all these papers actually also from Nature Baby papers, okay, like all the other top journals. So we compare with them, we are one of the highest one. Okay, and also because of this, so we write together a review paper with Professor Detro from France, and we trying to review how can we align this 1D, we call it a 1D structures, okay, align it on top of substrate. So you can see we are here. we have summarized 14 altogether. We are the number 14, which is the new way. Okay, so if you're interested in this one, you can talk to us. So we will help you. It's very easy. You just need to use a magnet. So you can just spin your silver nanowires, whatever wires, maybe CNT also. We never try it, trying to align it, because once the nanowire get aligned, right, you can get whatever anisotropic properties. Okay, so I summarize here. So I edit this book, vanadium dioxide-based thermochromic smart window, and our work have been highlighted by Nature here. So they report our work, and it has been reported widely by Reuters, World Economic Forum, NTFP, South China Morning Post, and the YouTube. NTU make a video. YouTube, the viewer is more than 20K. Okay, I'm quite surprised, since people say, hey, this is something very think out of box, right? So, and also my colleagues and my friends, some of them have left us, but they are all my best friends without them. So you can see there's a journey. You can see it's not easy. Start with one researcher, with one PhD student. After 10 years, we become the leading scientists in this smart window research communities. And also these are my collaborators from all over the world. Prof. Shlomo, all these are Israel. My funding is in collaboration with Israel, Prof. Shlomo, Daniel Mandela, Prof. Ibrahim, and my friend in China and the US and Europe. So I never try her, but I enjoy just email them if I need anything. So all of you, if you want to collaborate with me, just drop me an email. We don't even need meet, right? I mean, 2/3 of them I never met. I just emailed them. I haven't met 2/3 of my collaborators. Okay, and so I personally like this one. So don't be afraid of boundless truths. So that you will never find the truth maybe, but there always exist joy in any step taken. Okay, so by one of my very respected scholar and the intellect. Okay, so because there's never ending, research is never ending, but as a researcher, we enjoy every little steps we have contributed to the research communities. And thank you very much. Thank you for your patience. Okay. Thank you. Thank you. Take care, everyone.
Thank you, Prof.